All right, we're in 9.4 now. We're getting close to the end of chapter 9. 9.4 is, I think, the shortest section in chapter 9, and it deals with a couple of types of identities that you don't use that frequently. They're all used at some point in Calculus 2. Calculus 2 is where we actually see a lot of these identities being used. But these particular ones are a little bit more specialized in where they're useful. And I will say this, of all of the identities that we talk about throughout chapter 9, and that's, the ones that we've already developed prior to chapter 9, the Pythagorean identity, even and odd identities, cofunctions, the double angle formulas that we talked about in 9.3, sum and difference identities, reduction formulas. There's a long list, right? Ultimately, you want to have all of those memorized. And I know that's a tall order, but you're going to use them so much from here forward that it's just kind of naturally going to happen anyways. The product to sum formulas and the sum to product formulas are the only ones that I really say don't bother memorizing those. Because again, they're complicated looking, but then on top of that, they are not used anywhere near as often as the other ones. They're very specialized in where they find usefulness. Not to say that they're not useful. And then on top of that, if you've seen how we derive these things, it's oftentimes easier just to derive them on the spot than it is to try to memorize them. So let's talk about what we're trying to get here. Product to sum formulas. What we're doing is we're starting with an expression that looks like a product of sines or cosines. So something like sine of alpha times sine of beta, or it could look like sine of alpha times cosine of beta, or they could be both cosines or whatever. But the point is that we're looking at a product of sines and or cosines. And the angles can be two different angles. Alpha and beta is what we're seeing here. What we want to do is find a way to take that product and represent it as a sum of trigonometric functions, sines and cosines in particular. Again, this is useful in integration. It is difficult in some cases to, I'm just going to say it's generally difficult to integrate a function that looks like a product of sines or cosines where the angles don't match. And you'll see why when you get to calculus. However, it's very, very straightforward to integrate sums of sines and cosines. So these formulas are putting expressions like this into a form that's ready to be integrated. Let me put it that way. All right, let's see how we do this. So what I'm going to do is take a look at my sum and difference identities. In particular for the cosine function. Cosine of alpha minus beta. Back in 9.2, we said that was equal to cosine of alpha times cosine of beta plus sine of alpha sine of beta. Cosine of alpha plus beta, our sum formula or our sum identity, looked almost identical but with a minus. Now because these two identities on this side look almost identical except for a difference in sign right here, it's worth thinking about what would happen if I added these together, like a system of equations. If I added these together, then the positive product of sines and the negative product of sines would cancel each other out. And I'm left with cosine of alpha cosine of beta plus another cosine of alpha cosine of beta. That's 2 cosine of alpha cosine of beta. On this side, the angles here aren't the same, so they're not like terms. I can't just combine them. It would just look like cosine of alpha minus beta plus cosine of alpha plus beta. That's this, okay? Now, if I were to divide both sides of this equation by 2, then I get cosine of alpha times cosine of beta equals 1/2 cosine of alpha minus beta plus cosine of alpha plus beta. This is the first of 4 product to sum identities or product to sum formulas. And notice we have a product of cosines on one side and then a sum of cosines on the other side. Notice we're multiplying by 1/2, but that doesn't really make anything more difficult. It's still a sum of cosines over here. We could derive the other 3 product of sum formulas using a similar technique. We would be looking at the sum or difference identities for either cosine or sine, and then adding or subtracting those things and simplifying. I'm not going to go through all of that because if you've seen one, you've essentially seen them all. But these, for reference, are all 4 of the identities that we're talking about for product of sums. So let's take a look at an example. Write the following product as a sum. 4 times cosine of 3x over 2 times sine of 5x over 2. Notice the angles don't match. They can match, but they don't have to. So 4 cosine of 3x over 2 sine of 5x over 2. Okay, what we're looking at here is a cosine times a sine. And that's this identity right here. Whoops, I scrolled down too far. Cosine of an angle times sine of some other angle is equal to 1/2. So this is equal to, let me keep the 4 out here, times 1/2 sine of the sum of those two angles. So sine of 3x over 2 plus 5x over 2 minus sine of the first angle minus the second. 3x over 2 plus, minus 5x over 2. And at this stage, we just simplify things. 4 times 1/2 is equal to 2. 3x over 2 plus 5x over 2 is 8x over 2, which simplifies to 4x. I get sine of 4x here. 3x over 2 minus 5x over 2 is negative 2x over 2, or just negative x, minus sine of negative x. And I could leave it that way, or I could use my odd identity for sine to pull that negative out, which would change that to a plus. 2 sine of 4x plus sine of x. And that's what we were being asked to do. We represented our product as a sum. Okay? And again, you might look at that and think that's great. I can't imagine why I would ever need to do that. But as I said before, if you're looking at integration, again, Calculus 2 topic, this is very, very easy to integrate once you know the techniques. This is very, very difficult to integrate. So this puts things in a form that's better for integration. Okay, here's another example. Use the product to sum formula to evaluate this. Yes, I could plug all of this stuff into a calculator, or I could use a half angle identity here and another one here. There's other ways to accomplish this than what we just did, but we're going to try using a product to sum formula specifically to do this. Notice 11 pi over 12, pi over 12, those are not angles that appear on my memorized unit circle. So I don't know what they are off the top of my head. But look at your, this is the identity that we just derived. 1/2 times cosine of the difference of those angles plus cosine of the sum of those angles. So cosine of 11 pi over 2 times cosine of 12, not 2. Cosine of pi over 12 is equal to 1/2 times the cosine of the difference between those angles, 11 pi over 12 minus pi over 12, plus cosine of the sum of those two angles, 11 pi over 12 plus pi over 12. Now we do the subtraction and the addition. So I get 1/2 times cosine. 11 pi over 12 minus pi over 12 is 10 pi over 12, or after simplifying, 5 pi over 6. 11 pi over 12 plus pi over 12 is equal to 12 pi over 12, or just pi. So I get plus cosine of pi. Okay, this is equal to 1/2. Both of these angles are on my unit circle, my memorized unit circle, and so I can just evaluate these directly. What is cosine of 5 pi over 6? That's in the second quadrant where cosine is negative, specifically negative root 3 over 2. Cosine of pi. Cosine of pi is equal to negative 1. So I'd get minus 1. And then I could either leave it in that form or distribute. So I would get negative root 3 over 4 minus 1/2. I'm content leaving it that way. I could also, get common denominators and everything, but I don't see a reason not to leave it in this form. Cool. So like I said, this is a short section. We're already halfway through it. We talked about the product to sum formulas. It sort of makes sense to ask, would you ever want a sum to product formula? In other words, can we take a sum of sines and cosines and find an identity that converts them into a product of sines or cosines? And yeah, there is occasion to want to be able to do that sometimes. So that's what we're going to do next, develop those formulas. Like we did previously, it turns out that when I say previously, I'm talking about when we developed the half-angle formulas back in 9.3. It helps to use a variable substitution. So we're going to be working with the variables alpha and beta, but we want to make a substitution for these. And it's not going to be immediately obvious why we're using these in particular, but just sort of stick with me and you'll see how I apply them. Alpha, I'm going to set equal to u plus v over 2. U and v are new variables that I'm defining just for this purpose. Beta is going to be defined similarly, but with a minus instead of a plus. Okay? So again, alpha is equal to u plus v over 2. Beta is equal to u minus v over 2. If I were to add alpha and beta, alpha plus beta, that would look like this: u plus v over 2 plus u minus v over 2. The sum of these two things, they have common denominators. The v and the negative v will cancel out. U plus u is 2u, and 2u over 2 simplifies to u. So it's simplified down by a lot. Alpha plus beta is equal to u. If I do something similar and do alpha minus beta, following similar steps, that simplifies down to just v. Okay? Now again, it probably doesn't seem clear why we are doing this at all. Here's where we're going to make this useful. We're going to take one of our product sum formulas that we've already developed. In this case, sine of alpha cosine of beta equals this: 1/2 sine of alpha plus beta plus sine of alpha minus beta. Because those identities involve a sum of alpha and beta and a difference of alpha and beta, that's where these substitutions are going to be useful. So the alpha plus beta can be replaced by u, and the alpha minus beta can be replaced by v, the way that we've defined u and v. Okay? So that's what's going to happen on the right-hand side. Now the left-hand side is going to get a little messy looking, because again, the left-hand side of this identity only had alpha or beta as the angles that were being used. And those are going to look like either u plus v over 2 or u minus v over 2. So those get a little bit messier looking, but still not the worst thing in the world. Finally, I'm going from this step to this step. We also multiplied both sides by 2 to eliminate the 1/2 on this side. And this is the identity that I ended up with. Now, even though we have u's and v's here, that u and that v can be replaced by anything. And since we kind of like alphas and betas when we're talking about angles, we're going to replace the u's and v's with alphas and betas again when we restate our identities right here. Okay? But the identity right here is the one that we just came up with. Sine of alpha plus sine of beta. Again, it originally said u and v, but I can call them anything that I want. Sine of alpha plus sine of beta equals 2 times sine of alpha plus beta over 2 times cosine of alpha minus beta over 2. Okay, let's use these in a couple of examples, and then we're actually done with 9.4. It's a very short section. First thing I want to do, write the following sum as a product. Sine of 3x plus sine of x. So this is a sum of two sine functions, each with a different angle. It fits this form right here. Sine of 3x plus sine of x. According to my sum to product formula, this is equal to 2 times sine of the sum of those two angles, 3x plus x over 2, times the cosine of the difference between those two angles, 3x minus x over 2. And now it's just simplifying. This is equal to 2 times sine of, well, 3x plus x is 4x, and 4x over 2 is the same thing as 2x, sine of 2x. 3x minus x is 2x, divided by 2 would just be x, cosine of x. And that's it. See, there wasn't a whole lot to do there. It's just directly using that identity. Let's do one more before we wrap things up. We're going to prove an identity using the formulas we just came up with. Prove cosine of 3x plus cosine of x equals this big mess on that side. I'm going to start with my left-hand side because it looks like a sum of cosines with different angles, which matches this form right here. Cosine of alpha plus cosine of beta equals all that. So I'm going to use the right-hand side here. according to that identity, this is equal to 2 cosine of alpha plus beta, again, 3x plus x over 2. Yeah, that was it. Times cosine of alpha minus beta, or 3x minus x over 2. Looks similar to the previous example as far as the angles are concerned. So this gets simplified down to 2 times cosine of 4x over 2, which is the same thing as cosine of 2x. And then this becomes cosine of 2x over 2, which just becomes cosine of x. Okay? Now you notice it doesn't look like what we have here. But I do see a cosine of 2x here, which looks similar to a double angle formula, or makes me think of a double angle formula. We have a few double angle formulas that we know of for the cosine function, and I'm going to try using the first one. Cosine of 2x is the same thing as cosine squared of x minus sine squared of x. So this becomes this. Then I also have this cosine of x here. It's starting to look a lot like what we have. If I were to take that cosine and distribute it into the parentheses, then I have 2 cosine squared times cosine would be cosine cubed of x minus cosine times the sine squared of x that was already there. And that is what we were asked to prove. So even though this looked really complicated and really difficult, it really just amounted to using our sum to product identity for the cosines, and then once we did that, recognizing that there was a place where we could have used a double angle formula, and that's how we wrapped this up. Okay, so again, like I said, 9.4, very short section, but there you have it. We're almost done with chapter 9. 9.5 is going to be a much longer section. We'll address that next week.